Okay, so Friday, we talked about how to handle first order differential equations. So if I was talking about something like I said in my example, like a simulation engine, right? If I was going to solve a differential equation in a computer, again, this would just be like a circuit simulator. You guys have used those probably in circuits, right? To simulate a basic circuit. You obviously, it's not guessing a solution, right? It has to do it. It has to have some piece of code to grind through it numerically. Otherwise, that would be some sort of artificial intelligence, and clearly that's not, what's going to be happening. So how do we approach this? So what we worked out the other day was how that's done, right? And the big thing that we sort of described the other day is I gave this example. I got two things that are basically representing the same graph, right? So I said a continuous time function versus a discrete time function. What's the big difference between what I've written here and what I've written here? Yeah, this one has a delta t built into it, right? They're both functions. This is a function of time, right? So what is t here? What kind of number is t? T is what? It's a real number. This guy's a real number. What's n in this expression? It's an integer, right? So essentially what I'm talking about here in this discrete time function, if I plot them, right? Essentially what I'm doing is I'm plotting a series of numbers. So this was the example. These are basically the same response, right? The top is basically the continuous time, which I plotted versus time, whereas the bottom I'm plotting versus what I called sample number. So what I'm showing here is basically my values. They would be exactly the same, right? If I plugged in the n values here, I would get those time values that I had. Did I actually start the recording? I did. Yeah. All right. So this is a really important concept. They're the same sort of graph, but this is basically, I can't have x of t really in a computer, right? What I have to have is what I call the samples of x of t. And I can think of that as what I call x of n, meaning that if I try to index through that vector, I index through it by sample number, right? I say I want to look at the first point or the second point or the third point or whatever, right? I don't look at the value at a particular time. So we described that the other day, and I talked about how we discretize an equation. So discretize meaning to convert it from continuous time to discrete time by basically taking the definition of the derivative, right? So we said the definition of the derivative is the slope. So it's this whole limit as delta t goes to 0. So what did we say we wanted to do? If I have a derivative, I basically say this thing becomes what? Well, yeah, so what do I do with this expression here? So dy by dt becomes what? I don't keep it as the limit, right? What do I do with this? Dy by dt is what? So in the limit, what are we doing? We're making delta t go to 0. Can I actually make delta t go to 0? So in this graph here, where I said I got to jump from time t plus delta t. Yeah, so my delta t can't be 0, right? Because then I would have infinitely many points, infinitely many samples in that function. So what did I do? I said, well, make delta t small enough, right? Where basically I can say this guy is approximately y of t plus delta t minus y of t all over delta t. So it's an approximate statement that I make, right? And my goal is that for this to be true, delta t needs to be small enough, right? That very scientific term, small enough. All right. So how do we determine how small? Well, we did an example the other day where I plotted it. And I mean, as delta t got smaller, we saw that the error, right? So there was an error between the actual function and the approximate. In other words, this process is going to give us an approximate answer. It's not going to give us an exact answer. but it's close. It should be close enough that I can't tell the difference. And if they're not close enough, then my delta t value is too big. All right. Ideally, so what? Again, let's just to understand, what would be our ideal delta t? What would be the ideal choice for that delta t? 0. Right. The ideal choice for my delta t would be that it was equal to 0. That would be the ideal. But that means that every time I step, I'm really not stepping at all, right? That's something that only Newton can really think about in his limits, right? If we want to do something real inside the computer, we got to make some kind of a finite jump. We just need to make sure that jump isn't too big. If my jump is too big, I can actually get a completely wrong answer, okay? And that's one of the problems that we'll run into, which we'll get to an example of that today where I choose that, where it's just wrong, okay? All right, this is an important point. Today we got to deal with this idea of small enough, okay? So to do that, we're going to do that specifically today with the second order equation. How would I deal with a second order? Well, this guy is a little trickier because I guess I could go back and I could look at the limit as delta t goes to 0 for a second derivative, but that's going to get pretty nasty pretty fast. So what I'm going to do instead is I'm going to say, how can I think of a second derivative? What's another way to think of a second derivative? What's that? A second derivative is what? It's a derivative of a derivative, right? It's the first derivative of the first derivative. It's the rate that it's the acceleration, right? It's the rate that the velocity is changing. So I could write this a little bit differently. I could say I got d by dt of dy by dt plus b times dy by dt plus c times y of t all equals x of t. All right, those two expressions are exactly the same, right? Nothing different about those two. So here's the fusion. I brought with me a piece of paper. Well, I had some numbers written on it, so, but that's let me just keep going with this. All right, so with this expression right here, what I'm going to do is I'm going to look at this and I'm going to say it kind of looks like I've got three things here, right? Three functions of time in this. The three functions of time that I have in here, one of them is x of t, one of them is y of t. There's another function of time in here, right? Isn't there? So x of t is a function of time, y of t is a function of time. So too is dy by dt. All three of those are functions of time. So what I'm going to do is I'm going to say right now, I'm going to say let dy by dt. I'm going to write this a little bit differently. I'm going to make two definitions. I'm going to say let y1 of t be equal to y of t. Okay. Now I'll write this down a little ways and give myself some space here. So let y1 of t equal y of t. In other words, I've just renamed y1. No big deal about that. The other thing is I'm going to say dy1 by dt. I'm going to define another variable, y2 of t is equal to dy by dt. Or using this definition, dy1 by dt. Like that. All right. So if I do that, I'm going to rewrite this first in terms of the y1 variable. So I'm going to say this guy becomes d by dt of dy1 by dt plus b times dy1 by dt plus c times y1 of t equals x of t. Like that. All right. And I'm making these definitions here. Now, I'd like to, I can't move all those together. I can't. I wanted to move those somewhere. How can I rewrite this expression here? Well, I can say that this is the same thing as d by dt. So everywhere I have a dy1 by dt, right? What can I replace that with using these definitions? y2, right? So I can say this is dy2, like that, dy2 plus b times y2 plus c times y1 equals x. I'm just removing the of t's here real quick, right? So what I did, so in jumping from this line right here to this line right here, all I did was plug in the fact that I've made this definition that y2 equals dy1 by dt. Okay. All right. So what I'm going to do is I'm going to rearrange that. And I'm going to say that I have dy2 by dt equals x minus b times y2 minus c times y1, like that. Okay. All I did was rearrange this expression, right, where I brought the by2 and the cy1 to the other side. All right. And then I'm going to take this other expression that I have here, which is that y1 y2 of t equals dy1 by dt, like that. All right. So two expressions here. No, those two expressions, if I look at those, x of t is my input, right? That's something that's going to be known to me. If I give you a problem, I'm going to have to give you what the input is. If I look at this, this is basically a system with two equations, right? And how many unknowns? Two unknowns. Okay. What are the unknowns? They're y1 and y2. What's true about these two equations? Are they second order now? They're both first order. All right, these are both first order equations. So in other words, what I can do is I can approach each of these like they're both first order equations and turn it into a system of equations. All right, so basically these, so here's the two results. I just rewrote them over here, right? So to discretize them basically means that I make that jump that I say d, in this case, I'm going to say specifically dy1 by dt, I'll write it down here, dy1 by dt is approximately equal to, I put it in the definition of the derivative, right? If I put in the definition of the derivative, what do I have here? What over what? How do I write that? Yeah, y1 of t plus delta t minus what? So we said this is like rise over run, right? So the run, the change that I make is delta t. Yep, right? So basically I'm saying how much of a change vertically happens, right? That's the y1 of t plus delta t minus y1 of t over how much change happens horizontally. That's the delta t. And then I have similarly for the y2 variable, I can make the exact same expression. All over delta t like that. Okay. All right. So if that's what I end up doing, and I try to use this result, I can use that result here and I can plug these two expressions into those two equations I have. So I can turn this into, for the first equation, I can say it turns into y2 of t plus delta t minus y2 of t all over delta t equal to x of t minus b y2 of t minus c y1 of t. Right? That's doing this for the first equation. I do it for the other equation, it becomes simply y1 of t plus delta t minus y1 of t all over delta t equals y2 of t. All right, now I'm in derivation mode and you're going to fall asleep fast, right? So what do I got to do? The important thing is, in discretizing, what have I done? What's that? Well, so I was already first order here, right? But I jumped from a calculus world, right? The important thing is over here, I got calculus. What do I have over here? Yeah, I got algebra. All right, that's the important thing. One set's approximate. These guys are exact. These guys are approximate. And our job is to make sure the approximation is good. All right. That's what I'm more concerned about. I don't want to spend too much time here on derivations. Right. So what do I got to do? Well, basically what I have to do is the same sort of thing I did the other day. I want to get to an expression. I want to simplify these down so I get an expression for y1 of t plus delta t and y2 of t plus delta t. Right. So in other words, I can just rearrange the algebra there, which I don't want to go through. Basically, what I end up with is those expressions, right? So if I take those two previous expressions, I take this one here, and I'll put it looks like a minus sign. If I take this expression here and this expression here, they become those two things, right? If I rearrange to do the algebra. So what this is saying is, so y1 of t plus delta t is equal to y1 of t plus delta t times y2 of t. What the heck does that say in words? What is it? When I said t plus delta t, what did I say was true about that? What? So t is equal to now, right? That's the current time. Where is t plus delta t? The future, right? It's going to become a Spaceballs conversation here. All right. Now is now, not the future, right? So I have now and the future. So the way that we said this is basically, given the way that I set up my time, time is always n times delta t, right? So n is like the count of the time steps, right? So if I gave you, we did this the other day, right? If I had a vector n, and I said n goes from 0 to 1,000, and I chose a time step, my time vector would be that n vector times my time step. Okay. So how did I write this? I said in the computer, I don't do it like this. I write a discrete time version of this. So what I end up saying is, I can plug in here, I can say y1 of n delta t plus delta t equals y1 of n delta t plus delta t times y2 of n delta t. Now, looking at that expression I just wrote down there, is there any t here? Right? What I said was, I don't even really need to have the delta t's in these expressions, right? I could say instead that the next value, the n plus 1th value in the vector, right, is equal to y1 of n plus delta t times y2 of n. I guess the way that I can write this is, let me do it this way. So t is equal to n delta t. We said this is now. This n delta t plus delta t, which we can see is n plus 1 times delta t, is the future. So the way I relate this is I say the next value in the vector, y1, is equal to the current value in the vector plus delta t times that. This is basically, you know, if the equation was linear, like this is kind of like saying, right, if I had a a line like this, right? And I know the slope of that line, then I can just say the next value is going to be whatever my current value is plus the slope times the time, right? It's basically what this is saying, all right? So we got to make sure basically that our approximation is that the slope really does represent the amount of change that's going to happen. That's making sure the delta t choice is good. All right, I can do the same thing for that y2 equation. I get y2 of n plus 1 equals this, just copying that over, x of n minus b times y2 of n minus c times y1 of n, all times delta t plus y2 of n is what it ends up being. All right, I got two equations and two unknowns. The two unknowns that I have at any time step are basically what the future values of y1 and y2 are going to be. All right, now, what's going to confuse you later is we just did a bunch of math, we wrote some equations down. What the heck was I trying to figure out in the first place? Well, yeah, I'm glad I asked. I want to figure out the value of delta t to make this all work. But what was the answer? What am I trying to do? I'm trying to solve a differential equation that started out like this. So the important thing for us to remember is that y1 is equal to y. Y is the output. The thing we are solving for at the end of the day is this guy. Right? We are solving for y1. Y1 is the actual output. But to make it work, I got to solve for its derivative as well. That's what the y2 is. So I got to solve for them both. All right. That's the part that's going to screw you guys up later. Right? Now, the other part that's going to screw up later is the time step, right, which I keep saying. But at the end of the day, this is what I got to do. All right. I got to figure out how to break up the equation this way. Okay. So our approach with this guy is going to be two steps, right? First is I got to create the equations, discretized equations, right? There's going to be, if it's second order, there's going to be two of them. Okay. Then I got to figure out the appropriate time step. So what I'm writing out here is to figure out the time step, I got to figure out really the critical thing is the relevant time domain features. Because what's important to me, right? So like if I had a first order system, okay, like I have that response. How would I, so what's the relevant, when I say relevant time domain feature? With the first order thing that basically rises up exponentially and then levels off, what's the relevant time domain feature that I want to see when I make the graph? Yeah, I want to see the exponential part, the e to the whatever t, right? This is the key part. So I got to be smart about that particular feature to make sure it gets represented well, right? So this part's the transient part, right? So if I said to you, all right, so how long does a transient last for? So if I have an exponential transient, you guys told me this the other day. How long does an exponential transient last for? 5 to 10 tau. So let's say it's 5 tau. All right. So it lasts a span, a time span, meaning from here to here maybe is about 5 tau. All right. So what do I have to make sure of with my choice for my delta t? How would you, if I want to make sure that I capture that entire sort of changing period right there, what do I have to, how would I think about my delta t? Yeah.
4 5 towers from 0. That's 0.
Well, yeah. So my delta t, my time step, my step between points, right? So like basically saying like, okay, I start at t equal to 0, and then I go here, and then I go here, and then I go here. I got to make sure that time step is small, right? How small should I think it is? If I want to capture that entire 5 tau, small enough, okay, sure. But how small is small enough? You give me a better guess as to small enough. Tau over 1,000. I like that choice. What you're saying is my delta t, so I just put two less than signs. Is that what I wanted? No, I wanted two greater than. What the heck does that? Let me write it. Actually, I'm gonna write this way. Delta t less than less than. What the heck does less than less than? You ever seen that before? Much, much smaller than 5 tau. Yeah, basically negligible. Now the question is, what's negligible? It depends on the problem now. Because what's tau? Tau depends on the system, depends on the problem, right? So the values could be different. So this says much, much less than. All right, and that is a pretty common thing in engineering to use, right? That terminology, much, much less than. All right, so got to look at this, and when I do this, I got to say, well, I got to look at the steady state response and the transient response, and I got to figure out what are the relevant time domain features I got to look at. Now, the problem I got here is we're talking more about the choice of the time step on Wednesday, but if I look at this, I got two choices here: decaying exponentials, right, and sinusoids. That transient response, if I have a second order system, could look kind of complicated, right? Because it's got an exponential times this decaying, or an exponential times a cosine, right? So I got some stuff to think about. The first order system is pretty straightforward, right? But it's a little bit less so if I'm talking about a second order system. And I also got to think about what the steady state response does, okay? Now, the steady state response, if I just had something that was leveling off to a constant, well, that doesn't require much thought at all, right? But something where I have a lot of change going on, like that exponential, that's something where I got to give it some careful thought. All right, so let's do an example here. My first step was to basically say, all right, I need to figure out how to discretize the equation, okay? So what I did was I said what? I said, well, I need to rewrite this guy. So I have d squared y1 by dt squared plus 4 dy1 by dt plus 100 y1 equals u of t. But instead of writing it that way, I'm going to say equals 1 for t greater than 0. Okay, that's an equivalent statement. And what I did here was I said y1 equals y. Now, what was the other statement I said? I created a variable y2. And what was y2 equal to? What was it? What was it? Oh, yeah, it's the derivative. Yeah, there we go. All right, so derivative. So I rewrote this guy and I said I got the derivative of the derivative plus 4 times the derivative plus 100 times y1 equals 1. And then I had the other expression, which was that y2 equals dy1 by dt. Right? These are the two equations that I have. Okay. So I convert those two equations into the two discrete time equations, which are basically here. Right? So without going through all the math of rearranging those, I get them basically into that form. And if I put them in really in the real discrete time way, what do? I get rid of t, right? So instead of saying t plus delta t, I say y1 of what? Not of t plus delta t, but of n plus 1 equals y1 of n plus delta t times y2 of n. And I have y2 of n plus 1 equals, in this case, x of t minus, so x of n minus 4 y2 of n minus 100 y1 of n, all times delta t plus y2 of n. Now, the 4 and the 100 basically come from these values here, right? But what about this x of n, right? Do I need to leave the x of n in there? What's my x of t in this system? U of t, right? So it's just 1. So I'm going to write this guy, instead of saying x of n, I'm going to put the number 1 right there. All right. Now, for what I gave you in the homework problem, which I guess is officially due tonight, right? I gave you what delta t was, right? The thing that we got to get to now is this step 2, which is how do I choose the time step here? So to choose the time step, the way I got to look at this is I need to really think about this problem a little bit. I need to think about what are going to be the relevant time domain features in this system. So I said basically what that means is I got to think about the steady state response, and this is actually, to me, this what I'm about to do is a lot more important than knowing how to solve the differential equation by hand anyway. I want you to be able to tell me intuitively what's it going to look like. All right. Which basically means tell me what's the steady state response going to look like and what's the transient response going to look like. I don't want to go through the whole process of solving everything, but I want to figure out what are they going to look like. So how do I do that? What's the steady state response going to be? Yeah. The homogeneous is the transient. Yeah, so without getting to a specific number here, what's the steady state response going to look like? If I told you describe it, what it looks like to me, what's it look like? Yp of t is equal to a what? Is what? A constant. And yeah, that constant, if I substitute it in, it's going to be 1 over 100, right? It's just a constant number. All right. Is there any interesting time domain features to that? No. For this, I could choose a delta t that was, infinite if I wanted to. I could choose a really big delta t. All right. This guy doesn't matter. This does not affect my delta t choice. I know that now. Because it's time, I'm gonna write this, it's time domain features. Its time-based features are uninteresting. Uninteresting. Like that. Okay. The transient response, in other words, uninteresting. There aren't any. Right? It just basically at time t equal to 0, it's a constant, and then it stays there. What about the transient response? What's the transient response going to look like here? How can I figure out what the transient response is going to look like? Well, I know that it has to be some exponential, right? Like that. But tell me more about that, because those exponentials can look different ways, can't they? Right? How do I figure out what kind of exponential I'm going to get? The roots of that characteristic equation. So what's the characteristic equation for this guy? S squared plus 4s plus 100 equals 0. Yeah. Okay. So beyond that, I do need to go farther and actually kind of figure out what the roots are. But looking at this, what kind of damping do I have here? Underdamped, overdamped? Underdamped. Underdamped. Now, the reason I can tell that right off the bat is I can say my roots, if I go to my characteristic equation, I'm going to have minus 4 plus or minus the square root of b squared minus 4c. So 16 minus 400. What told me it was underdamped? Yeah, whatever is under the radical, the b squared minus 4ac, right? Now I've got what number that is here, and I'm going to pull that down in a second. It's going to be -2 plus or minus j something. Okay. When it's underdamped like this, right? What's that mean? We gave a kind of a general form to what that's going to look like, right? What's the general form when it's under damp? What's the general form of what this guy is going to become? Well, don't worry about the specific. So what's it going to look if I told you what's it going to look like? Not just a cosine. But yeah, okay, he gave me it's a decaying cosine.
Yeah.
It's a smushing cosine. All right, I like that term. All right, so it looks like this. All right, this I took back to my specific values here, where I said basically, and I have this in the notes for just for whatever back in. I got to be careful here. I think to be totally consistent, I have it sigma plus minus j omega d, right? Like that. Now that sigma value is always going to be negative, right? Which it was in this case. If I go through the math here, the way I always do this, I said I use this roots function, right? And I get the following here. So my sigma is equal to -2, and my omega d is apparently 9.798 radians per second. Okay. Now, I got to ask myself some more questions about this guy, right? Now, what did I do here? Basically what I did is I said I converted this over so it had a e to the -t over tau look to it, right? I did that because I know that if I have an e to the -t over tau, what's the important time feature here? I said, if I have an exponential, what's the important time feature? Well, I said, basically, this guy ends in 5 tau. Right? So I needed to make sure that I captured that entire transient piece. Now, cosine omega d times t, that guy's important too, isn't he? So cosine omega d times t. And there's an angle to it. The angle isn't that important. What would if I wanted to see the cosine properly, what do I got to choose from my time vector? How do I always tell you to choose your time vector when I tell you to in your homework? A lot of points. Yeah, that's true statement. A lot of points. What do I usually say about your time vector? What value do I usually ask you to do? T over 1,000. Yeah, basically what I do is I ask you how big's a period, right? So T, and then make sure that your time step is much smaller than that, right? So basically here, the key feature is the period, which I'm calling T sub D in this case, all right? So basically the important features to me are the period of this cosine and how long it takes for that exponential to decay, all right? And from there, I can split this guy up. Right. So what I do is I say, all right, I got two possibilities to capture this whole thing. One possibility is that I want my delta t to be much, much smaller than 5 tau. The other possibility is that I want my delta t to be much, much less than what? So then a period, right? Which is basically 2 pi over omega d. All right. Now, the annoying part, I said I had a piece of paper. The piece of paper had those numbers on it, right? For this particular problem, right? My delta t could be much, much less than 5 tau. So what's my tau here? So my sigma value was -2, right? Tau is going to be 1 over that. So what's 1 over 2? Well, 1 over 2 is 0.5, right? So that means that this guy should be much, much less than 5 tau, or 5 times 0.5. What's 5 times 0.5? 2.5 seconds. So my delta t should be much, much less than 2.5 seconds. Okay. Delta t should be much, much less than 2.5 seconds. Now, what's much, much less than?
0.0001.
Well, yeah, this is the hard part. So usually what we'll say is factor of 100, 1%, right? So if delta t is, let's say, less than, and this is arbitrary, right? But I say that if it's much, much less than would be if it's less than 1% of, let's say, right? That seems like a reasonable choice. Now you guys don't like this at all because the system's taught you wrong, right? This is engineering now. Engineering, I got to go with my gut. My gut tells me, yeah, that's probably a good choice, right? Because it's 1% of it. That seems like a small amount, right? Right. So there's no exact answer to this, but that seems like I could choose it smaller, right? I could have divided by 1,000, right? That would probably work as well. So that would give me what was that? 0.025 seconds, right? So I moved that over a certain amount. Okay. Now, what was my other value? 9.798. All right. So do this my calculator here real quick. Since I didn't bring it with me. So 2 times pi over 9.798. Is that what I had? This guy is one period of this is apparently 0.6413 seconds. So delta t should be much, much less than that. So what's much, much less than? Well, what did I say we choose to be much, much less than? 1%. So let's divide that by 100. That turns this into 0.006413, like that. Okay. So this tells me that my delta t needs to be less than 0.025 and less than 0.006413. So what should I choose? The smallest of the two, right? The smallest of the two, right? The smallest of the two, the smallest one that's going to capture all of the relevant time features. So I did that. Okay. Here, what I did was I said my delta t is this. Now notice what I did is I put my two equations here into my for loop, just like I did the other day. Right? It's no different except there's two equations in my for loop. The other day there was one equation in my for loop. And I plot it. And it looks more or less like I thought it was going to do. Like it ends up at a number really close to 0 because the particular solution is 1/100, right? What if I chose the wrong time step? So here I chose the wrong time step. All right. What do I notice about that result? It's larger. That's unstable, right? That's unstable, right? Now that's not what a real system would do. You know that. But if I choose the wrong time step, it's gonna behave unstably, right? So my computer can give me can give me a bad solution if I choose a bad time step. The part that's hard about this, and the part that you don't like about it, is what am I doing? I'm trying to rely on your intuition about what it should look like to make your choices. That's where this turns into the project, right? So now you're going to have to use your intuition about, so I'm going to give you real problems, and you're going to have to use your intuition based on what I give you in the real problem to make your choices. And then you get to code it up. All right. And there's all sorts of real world applications of this, right? One could be a simulator like I'm talking about, right? That's some of the problems I'll give you. The other one could be, I have an audio signal or something like that I need to filter, all right? In other words, I need to pass that audio signal through some kind of a differential equation to clean it up a little bit, right? So that's one thing that you'll play around with. So you got to figure out how to make those sort of time step choices. Okay. All right. That is it. All right. So you guys